Hello, I would like to welcome you to lecture 28 of 2FH3. We'll wrap up chapter 9, this lecture of the book of Sadico. We'll talk about vector potentials and time harmonic fields, and we'll cover chapter 9, pages 417 to 429. Most of the material covered in this chapter you have already covered before in circuit theory, because you talked about phasors, you understand what's meant by a phasor. So really the new content hopefully will, in terms of the phasor, will not be that much. In the statics case, we agreed that the electrostatic potential V is given by integrating over the volume rho volumetric d volume. This will represent the point charge over 4 pi epsilon r. So this is the way to calculate the potential for any charge distribution. And we found out that the potential as well, the electrostatic potential, satisfies the Poisson's equation Laplace squared V is equal to minus rho volumetric over epsilon. So actually the solution of this differential equation is this integral. They are actually related. The solution of this differential equation is this integral here. It is the opposite. It is the opposite mapping, because this one will give you here the V in terms of rho V. And of course, if there is no volumetric charge density, this becomes 0, and this becomes Laplace equation Laplace squared V is equal to 0. We agreed in the electrostatics case that the electric field is minus the gradient of V. We agreed as well that in order to calculate the magnetic field, we can calculate an intermediate vector. We called it the magnetic vector potential. It's integrating over the volume of mu jd volume over 4 pi epsilon r. Of course, we wrote it as well for linear currents or for service currents, but this expression is more suitable because the volume case is the most general case, and here we are doing a volume integral, and here we are doing a volume integral as well. So you can see there is an analogy between these two integrals here. Mu has been replaced by 1 over epsilon. And this integral will give you 3 components, while this one gives a scalar. So every component in this vector is analogous to one here. Now, once you have calculated the magnetic vector potential, you can get the magnetic vector magnetic flux density vector B by taking the curl of A. Now the question is how to move these calculations that we did in the statics case and move them to the dynamics case, where the volumetric charge density is varying with time, where the current J is not steady, it's varying with time. So now we'll start to try to solve for the magnetic vector potential and for the electrostatic scalar potential when the charges and the currents are time varying. So we started by one of the curl equations of Maxwell. Curl E is equal to minus partial B partial T. In the statics case, curl E was equal to 0, but now because we have time varying magnetic field, this gives rise to an electric field. If we replace B by the curl of A, this is how we calculate B. B is equal to the curl of A. Notice that curl is derivative relative to space, while partial T is derivative relative to time, and these two are independent from one another. So what we could do, we could move the curl ahead and move the derivative relative to time inside the curl. So now if you take a look at this one, this is telling you that the curl of E is equal to minus the curl of partial A partial T. Or if you move this term to the other side and combine the curl expression, you get that the curl of the combined vector, which is E plus partial A partial T, is equal to 0. Before, in the electrostatics case, we had curl E only is equal to 0. Now we have another term which is related to the derivative of partial A partial T. So now the curl of E plus partial A partial T is equal to 0. And we know from vector analysis that when the curl of a vector is equal to 0, then this vector can be written as minus the gradient of a scalar function. So now we can define the electrostatic, not the electrostatic really, we call it the electric potential now, the electric potential V. So in the time dynamic case, we can define an electric potential V, but it's related to E through this expression here. So E is equal to minus the gradient of V minus partial A partial T. So what is this telling us? Is that the electrostatic, the dynamic field now, not the electrostatic field, the dynamic electric field can be generated in two ways, either through time varying charges or through time varying currents, because A, as we agreed, is proportional to the it's obtained by integrating the current, and it's going to be in the same direction of the current. So now in the dynamic case, the dynamic electric field can be generated either from the electric potential, which is resulting from time varying charges, or from the time varying currents, when these currents are represented by the magnetic vector potential A. So now this is a fundamental change from the electrostatic case. E is not equal to minus gradient V anymore. E is equal to minus gradient V minus partial A partial T. So if you want to calculate to get the electrostatic, the dynamic field or the electric field, we have now to solve for two vectors. V, a scalar, have to solve for two potentials. A scalar potential V and a vector potential A. Solving for these two will result in the electric field. So now we'll attempt to change Laplace or Poisson equation to get an equation that applies for the dynamic case as well. We know that divergence D is equal to rho volumetric, and this expression is valid for the static case and for the time varying case. So we can replace D by epsilon E, and then if epsilon does not change with space, we can take it out. So we can now say that divergence of E is equal to rho volumetric over epsilon. But we know that from the previous slide that E is equal to minus gradient V minus partial A partial T. So we can simply say that E is equal to minus gradient V minus partial A partial T. Now if we apply the divergence to both sides, the divergence of this term will be equal to minus nabla squared V minus the divergence of this vector. But the divergence again is a vector operator. We are differentiating relative to space, and this is the derivative relative to time, so we can move the divergence inside the time derivative as shown here. So now what we're able to obtain here is that we have one equation that relates the electric potential to the volumetric charge density, and this equation is simply nabla squared V plus partial T of the divergence of A is equal to minus rho volumetric over epsilon. So now the problem with this equation is that it's different from the Poisson equation, is that we have another vector here. We'd like to obtain one equation where there is only V and its derivatives relative to space given by nabla squared, and derivative relative to time given by partial T. So we have to get rid of this divergence of A. And the only way of getting rid of this divergence of A is through using the second Maxwell equation, the second Maxwell curl equation, which is the curl of H is equal to J plus partial D partial T. We multiply both sides by mu, then this becomes a curl of mu H, which is B. This becomes mu J. We take D here, we write it as epsilon E. So we can take epsilon out, then becomes this term becomes mu epsilon partial E partial T. So starting from here to here, what we did is that we multiplied both sides by mu, and then we wrote D as epsilon E. So we end up with this equation. Now we know what is E. E, we already agreed, is going to be given by minus the gradient of V minus partial A partial T. This is a modified expression for the general dynamic case. So now we have one equation. It contains derivatives relative to space, double derivatives, so second order derivatives, and derivative relative to time. We'll use one very famous vector identity to replace the curl of the curl by the gradient of the divergence minus nabla squared. This is a very famous identity used very often in wave equation. So I replace this term here, which is the curl of A, by the gradient of the divergence of A minus nabla squared A. So we use this vector identity, the one shown here, and then we substitute. We end up with this expression here. It's pretty lengthy. This is the left hand side and this is the right hand side. We have here the gradient of divergence of A. We have here mu epsilon gradient of partial V partial T. Now, because A is only defined in terms of the curl, we know that curl of A is equal to B. But the curl does not uniquely define a vector. We have also to impose another condition on its divergence. This is known in vector analysis, that the curl of a vector does not uniquely define a vector, because you have to integrate both sides to get all components of A. But this integral will not be unique unless you know also a condition on the divergence. So what you said, okay, why don't we equate this term here, which is a gradient divergence of A, to this term here, which is the gradient of partial v partial t, and eliminate these two terms together. So what we'll do now is that we'll go back, and then we'll apply this condition, and then I will eliminate this term here with this term here. So I will impose the condition that divergence of A is equal to minus mu epsilon partial v partial t. Of course, there is no gradient here. There is no gradient in this part. This is a typo. So we impose the condition that the gradient of divergence of A is equal to minus mu epsilon multiplied by the gradient of partial v partial t, or that the divergence of A is equal to minus mu epsilon partial v partial t. This is called the Lorentz condition, and when you impose that, what you did, you eliminated v from the equation governing A. So now the equation governing A is minus nabla squared A is equal to mu j minus mu epsilon partial squared A partial t squared. And when I go back to the equation governing V, and then I eliminate the divergence of A, I'm able to obtain this expression. So now what I did, I was able to write two differential equations. One of them governing the electric potential, nabla squared V minus mu epsilon partial squared V partial t squared is equal to minus rho V over epsilon. And the second one is governing the magnetic vector potential. And of course I can move this term to the other side. It becomes simpler. So in the static case, this term becomes 0. This becomes Poisson's equation. In the static case, this term becomes 0, and then you get that nabla squared A is equal to minus mu j. This is how we really solve for A. So now what we're able to do, we're able to write two differential equations in terms of the sources. And the sources here are the volumetric charge density and the current that we have. So once you have this you have these two independent equations, you can solve them if you know rho v, if you know g. And by the way, these two equations are wave equations. As we'll see later, they represent waves traveling in space with velocity equal to 1 over square root mu epsilon. So really everything now becomes a wave. It takes time to propagate from the point of excitation until it reaches its target. So to summarize, what we're able to show here through using the two Maxwell curl equations, that we can write two differential equations with space derivatives. So we have space derivatives here, and we have time derivatives here. The first equation governing the electric potential. And you can solve for the electric potential in terms of the charges everywhere if you know them as a function of time. You can solve for the magnetic vector potential if you know the current G as a function of time. And these two equations, you have this solution. And now this solution is a little bit different from one that we have seen earlier. Because I'm saying here that the electric potential at time t is obtained from the charge at a previous time t dash. And the reason is that every V now is a wave. If you make a certain perturbation in space at one point, it will take some time for this perturbation to change the potential at another point. So this, if you know the distance between them r, and the wave travels by velocity of u, then it will take a time shift of delta t for this perturbation to travel from the location of the source, which is the charge, to the location of where I'm measuring the potential V. This is why now we can say they are at the same time. There is a time shift between them, and this time shift is this one here. It is the time the wave will take to travel from the point where the charge is to the observation point, the point at which you are measuring the potential. So now we call these potentials, we call them retarded potentials, because they take time from the moment the charge changes until that change starts to affect the potential in another point in the space. Of course, u here is a very large number. For free space, it is 3 × 10⁸ meters per second. This is why electromagnetic waves travel in a very fast speed. This is speed of light. The same thing is happening for the magnetic vector potential. The solution of this differential equation is a wave equation. The solution of this one is a wave. And you are saying that the magnetic vector potential at any point in space at time t is obtained from the current at a previous time. And the shift between time t and t dash is simply the time the wave will take to travel from the point where the current is to the point where I'm measuring the magnetic vector potential. These are called retarded potentials. And of course, once you know V, once you know A, you can obtain the electric field everywhere in the space. The second part of this lecture is how we solve for the time harmonic case. If all the charges and all the currents are sinusoidal with the same frequency, then the electric field will be as well sinusoidal. The magnetic field will be sinusoidal. All their components will be sinusoidal. So what we care about now is simply keep knowing their amplitude and knowing their phases. And this is why in the time harmonic case we care only about the phasors. For example, if you have a function of space and time like this one, f of x and t, it is 3 cosine omega t minus beta x. It's a sinusoidal function. It has frequency omega and it has a phase constant beta and the amplitude of 3. I can write this cosine as the real part of e to the j omega t minus beta x. I can separate the space and time terms, and then I don't really have to keep this time term. I don't need it. I know it. If I know the frequency, it's already given. It's already implicit. Then I take this term alone, and I call this term the phasor. So the phasor here is 3 e to the minus j beta x. And if I want to recover the actual time domain function from the phasor, I multiply the phasor by e to the j omega t, and then I take the real part to recover the actual time domain function. So if all our sources are sinusoidal, we don't have to really talk about time domain electric field, time domain magnetic field, time domain vector D, time domain vector B, and time domain currents. We can instead talk about their phasors. And these phasors are complex quantities. They are only functions of space x, y, and z. And if I want to recover the actual field as a function of x, y, and z, and t, I simply multiply the vector by e to the j omega t and take the real part. Notice that this vector has 3 components. This is a phasor of three the vector of 3 phasors, x phasor, y phasor, and z phasor. This as well as the vector of 3 quantities, x, y, and z. And every component will be multiplied by e to the j omega t, and then you take its real part. The same applies for h, for the phasor h and the time domain h, for the phasor d and the time domain d, phasor of b, time domain b, and so on. Even the charges. The charge at any point in the space, it can have its sinusoidal, then it has a phasor. I can talk only about the phasor. If I want to recover the actual time varying charge, I multiply by e to the j omega t and then take the real part. This actually simplifies the analysis in many applications where you assume all your sources are only sinusoidal. So if you have an antenna, and this antenna is connected to a sinusoidal waveform, it's only radiating sinusoidal waves. So everywhere the electric and magnetic field will be sinusoidals. They will have their own amplitude, they have their phases. I don't have to worry about the term e to the j omega t. I can add that later and then recover the actual time domain quantities. So by applying phasor analysis, we know that every time domain derivative can be replaced by j omega, and then we can write Maxwell equation in the time harmonic form. If you integrate the phasor of D over a closed surface, this will give you the phasor of the enclosed charge, which is equal to the volume integral of the phasor of the volumetric charge density. If you integrate the phasor of the vector B over a closed surface, this must give you 0. If you integrate the phasor of E over a closed contour, this will give you now the rate of change of the magnetic flux will give you minus j omega multiplied by the integral over the surface enclosed by C of B dot ds. This is exactly what we said before. It is minus partial t of B dot ds, but we replace partial t by j omega because we assume we're talking about one specific frequency. The same thing will happen to the Maxwell fourth integral equation. The integral of the phasor of the magnetic field over a closed contour is equal to the total current to the phasor of the total current enclosed, which is really the phasor of the conduction current and the phasor of the displacement current. This here is partial d partial t, which is replaced by j omega, the integral over the surface of d dot ds. So in many applications where we talk about one frequency, it is way easier to use phasors, Maxwell equation in the time harmonic case. And this, of course, these are the integral form. You can as well talk about Maxwell equations in the differential form, time harmonic. So the divergence of the phasor of D at any point in space equal to the phasor of the volumetric charge density. The divergence of the phasor of B at any point in space is equal to 0. The curl of the phasor of E at any time, at any point in space, is equal to minus G omega B, the phasor of B. This was minus partial B partial T. The curl of H at any point in space is equal to the phasor of the current density, which is equal to the phasor of the conduction current density and the phasor of the displacement current density. So these are Maxwell equations in the phasor form, both integral and differential. And in many applications, they simplify the analysis in a big way when you consider only one frequency and solve only for one frequency. Of course, same boundary conditions apply. So you can say the tangential component of the phasor of the electric field is continuous across the boundary between two materials. Everything that we talked about for the static case is moved again here in the time harmonic case. Let's take a look at one example. We have here a medium that has epsilon r equal to 16, mu r is equal to 1, and the electric field intensity is given by E of Z and T is 10 sine 10 to the power 10 T minus Kz AX. So the field, the electric field, is time varying. It's changing with position Z and time T, and it is polarized in the X direction. It has only one component in the X direction. This is, by the way, the expression of a wave, as we'll see later, maybe in advanced courses or later lectures. But we would like in this one, given this expression, I would like to obtain the corresponding magnetic field and the value of K. The corresponding magnetic field is not that difficult to obtain because we have two curl equations relating E and H. I can from them recover H if I know E, and if I know H, I can recover E. K can be obtained by knowing the fact that there are two curl equations. Then I can try to use them both together to solve for K, as I will show you in the next slide. I will use in this solution the time harmonic case. So this is a time quantity. It's 10 sine 10 to the power 10 t minus kz ax. I can simply write it as 10 multiplied by the real part e to the j omega t. Omega here is equal to 10 to the power 10 e to the minus j kz minus pi over 2. Remember that this is a sine, not a cosine. In order to make it a sine, I have to subtract minus pi over 2 here from the phase. So now we know that the phasor of this vector is equal to 10 multiplied by e to the minus j kz multiplied by e to the minus j pi over 2. Actually, I should, if I'm going to be putting it that way, I should maybe make this one plus here. Okay? Just to be consistent. I'm subtracting from the total phase minus pi over 2. So if there is a negative sign here, the negative sign multiplies both terms. So this is fine. So now we have, this is the phasor of the electric field. It's 10 e to the minus j kz e to the minus j pi over 2. And remember, e to the minus j pi over 2 is equal to minus j. So we can write this one as minus j here. So this is the electric field now. It is still polarized in the x direction, but now we're talking about its phasor. And now we talk about E tilde, the field in as a phasor. Of course, in the frequency domain or in time harmonic case, quantities are way easier to deal with. The curl equation is very simple. Curl of E is equal to minus j omega mu h, the curl of H. Then H is equal to minus 1 over j omega mu multiplied by the curl of E. Here we have only one x component, and this x component is only a function of z. So if you write the expression for the curl, you will see that you obtain only the derivative of the x component relative to z in the y direction. Okay, so of course you can expand the whole term, but I will show you only the term that I care about. So of course you can apply the curl of this one, and then this will be your h. So we write the expression for the curl, and if you keep only the non-zero terms, you'll see that you have to differentiate the x component relative to z in the y direction, and then you have to divide here by minus 1 over j omega mu. But this is ex. So when you differentiate this one relative to z, you get minus jk. Minus by minus will give you 1. J by j will give you minus 1. So you end up by minus 10k here, e to the minus jkz. And this in the y direction. Now, minus will cancel with minus. J will go to the numerator, becomes minus j. This is now the expression for the magnetic field phasor. You can see from this expression that the magnitude of this phasor is 10k over omega mu, and its phase, here you are multiplying by minus j. Minus j means you are multiplying by e to the minus j pi over 2. Then the phase of this quantity is really minus kz minus pi over 2. So we can put all this together, and then you see that your magnetic field will also be a cosine, but its amplitude is different. Its amplitude is 10k over omega mu cosine 10 to the power 10t minus kz minus pi over 2. Of course, if you substitute minus pi over 2, this becomes a sine. But of course, this magnetic field is in the y direction, so I'm here to talk about only the y component, this hy. So this is really the expression of a wave, and I explained to you earlier, an electromagnetic wave will have an electric field and magnetic field. They are normal to one another. In this case, one of them is in the x direction, the other one is in the y direction, and the wave is propagating in the z direction. Now I know h, I can solve for k. How can I solve for k? I have a second curl equation that I have not used. I used only that the curl of E is equal to minus j omega mu h. I can use that the curl of h is equal to j omega epsilon E. And then I can try from these two equations to solve for k. So using the other curl equation, the curl of h is equal to j omega epsilon E. This in the time domain where this was curl, h is equal to partial d partial t. And d is equal to epsilon E. So from this one I can say that E is 1 over j omega epsilon. We know everything here because h is already known. So h has only a y component, and it's only a function of z. So when you take its curl, you get only the derivative of the y component related to z in the minus x direction. So you differentiate this term here. After you substitute for hy and you differentiate it, you get another minus jk from the numerator. So anyway, so when you put the expression for h here, this is what you have. You have to differentiate this expression related to z and then divide by minus 1 over j omega epsilon, this in the x direction. I move this negative sign to the front here. So when you differentiate, j by j will give you minus, this one will give you minus jk again. Minus here will cancel with j, so this will cancel. And then you have this minus sign here. If you move the j to the numerator, this becomes minus j. And this is the expression that you will have for the E vector. Now we have two expressions for E. One that did not have any k, and this one as well in the ax direction. So there is one that was given as a phasor, and this one that we recovered. If we equate them, e to the minus jkz will cancel, and I have only one equation. I can solve it for k in terms of the omega, the angular frequency, the permeability, and the permittivity of the medium. If you equate the two equations for E that we have, you will get that k squared is equal to omega squared mu epsilon, or that k is equal to omega square root of mu epsilon. We know what's omega. It is the angular frequency 10 to the power 10. We know that epsilon is equal to epsilon naught epsilon r, so equal to 16 epsilon naught. We know that mu is equal to mu naught mu r, and here mu r is 1, so 1 multiplied by mu naught. So, and 1 over the square root mu naught, by the way, is a known quantity. This is the velocity of light. It's 1 over the square root mu naught epsilon naught. We take this one always at 310 to the power 8 meters per second. This is the velocity of light in free space. And this is what I did here. I moved, I took the 16 out. I took this 16 out. I moved, it became 4 outside. And then I replaced the square root mu naught epsilon naught by 1 over c, and c 310 to the power 8. So this will give you here that the phase term is 133 radian per meter. So this example shows you the strength of using time harmonics equations. We are able to deal with divisions rather than with dealing with integrals. When you differentiate, we simply multiply by j omega, and we have two curl equations that we can use to relate the electric field and the magnetic field.